Welcome back, and we are going to start our next invited talk. And the talk will be from Sara. And Sara is a research scientist at Google Brain, doing deep learning research on training models beyond test set accuracy to fulfill multiple criteria. Her main research interests gravitate toward interpretability, model compression, and the security, as well as the impact of design choices like hardware and the randomness on generalization behavior. She's one of the founding organizers of the Trustworthy ML Initiative, and in 2014, she founded Delta Analytics, a nonprofit dedicated to bringing technical capacity to help nonprofits across the world use machine learning for good. And let's welcome Sara's talk.
Thank you so much. So I guess this is why people have technical difficulties. They can have lovely introductions twice. But it's nice to be here, and thank you to all the organizers. So today I really want to chat about a topic that I find really interesting, which is can we leverage compression to tell us something about generalization? And in some ways, this is a bigger topic because it's this idea of what do different regimes of capacity give us in terms of generalization properties. So a lot of my work is on this topic. As Bill kindly mentioned, I work on designing deep neural networks that have desirable generalization properties, but are also efficient. And to understand why this is an interesting problem, it's good to understand how we got here. So we often treat performance of a model as synonymous with these top-line metrics. And typically that is just favored popular recipe of adding parameters to a problem. So we see that we get better top-line metrics with ever larger models. And this bigger is better race has gripped arguably our field. And this characterizes multiple different subfields. So there's an argument that I think is very strong to be made in support of this approach, which is that we are clearly seeing that at certain capacity regimes, we see distinct behavior emerging, and it seems to allow for different generalization properties. It's also a very simple formula, so we don't have to think too much about it. The constraint is in some ways the ability to scale efficiently, but given that, it's a clear direction or path in which to understand at least the cliff at which it stops being the case. However, I think a key limitation of simply following a recipe is that we actually don't have a good understanding of the relationship between weights and generalization properties. It's not well understood. And to talk about this, we have to talk about what's intriguing already, which is that when you pose the question, why do we need so many weights in the first place, the answer is frequently very unsatisfying. So we have diminishing returns to adding more weights. So we need millions of additional parameters to eke out additional gains. An example that I like is if you look at the difference between inception V3 and V4, you're just doubling the number of parameters, but you only are eking out about 2 percentage points in top-line accuracy gain. And there's many redundancies between these weights. So we can use a small holdout of weights to predict the majority of weights in a network, meaning that our weights are very correlated. And of course, what we find is that we can remove most of these weights once training is finished. So we can remove 90% of weights with very marginal impact. So the model is only leveraging 10% of its weights at inference time, but there's only a 3% performance drop. And even if you do a random, you're not losing considerably more. So random meaning you're just selecting a random sample of all weights to drop. And this is interesting for a few reasons. So there's theoretical reasons why this is interesting, because it suggests that our current representation format is very inefficient. And why do we need so many parameters to eke out these gains in performance? And it also begs the question of, if so many weights are redundant, why do we need them in the first place? Why can't we start with a smaller model? There's also a clear point of comparison, which is that we are remarkably efficient in comparison. So our own brain runs on the energy equivalent of an electric shaver. And we have multiple design choices that are baked in to enable efficiency. So we have specialized pathways, meaning that you can't read and walk as easily as you can walk and talk. We also simulate a lot of what we see. So we have this matching mechanism to make sure that we don't do full forward, backward passes for every input. And we have things like log scale vision to make sure that we only notice notable changes. In many ways, our assumptions in many of our models are more simplistic in comparison. We treat all examples equally. We do the same amount of passes for all of them. We do global updates, which can be really expensive once you scale because you're constrained by the need to update all your weights. And aside from those theoretical reasons why this is interesting, it's also interesting for practical reasons. So most of the world uses ML in a resource-constrained environment, and if we care about access to technology, we have to care about how difficult our design choices are right now in terms of making breakthroughs accessible. And this is largely because as you increase the size of your networks, you require more memory and higher latency. And most of the world is actually using ML at the edge. So the implications of rethinking why do we need so many parameters have extensions to, well, can we formulate a better design that is more efficient? And so this prompted the question that has guided a lot of my work over the last few years, which is how can these networks with radically different structures and number of parameters have comparable performance? And one possibility is that these top-line metrics are not a precise enough measure to capture how capacity impacts the generalization properties of the models. So here we go beyond top-line metrics. And in particular, we ask, how does behavior diverge as we vary the level of compression? And this is a useful mechanism to understand the role of capacity. So the first, to give you some context of what it means to sparsify a model, we typically talk about structured and unstructured sparsity. But unstructured sparsity, which allows you to achieve much higher levels of compression, means that you're removing individual weights by setting those weights to 0. There's a very active research field, even in this focus of how to sparsify, but most state-of-art methods introduce sparsity gradually over the course of training. But what this means and why this is a nice experimental setup is that you can predetermine the final level of sparsity. So you can train such that at the end of training, there's only 10% of weights remaining. And this means we can precisely vary the final level of sparsity. The other reason why this is an interesting setup is that sparse models easily outcompete small, dense models with the same parameter count. And this holds even for vastly less parameters. So for example, you can have a highly sparse transformer, 2.5 million weights, outperforms a tiny dense. This is also not particular to a certain subfield. So by looking at sparse models, we're able to look at a much wider range of capacity, but that has good models, that we're not looking at bad models and comparing generalization performance. And this is important because what we want to do is compare models which have radically different structures, but have similar top-line performance. And so we're able to compare even to very high levels of compression with minimal degradation. And that's what makes this interesting, because if there's minimal degradation top line with far less capacity, well, what is different? What are we losing? So to share some of the results of this work, what we found is that when you compress, you're actually disproportionately impacting a small subset of the distribution. And it's a small subset of both examples and where there's clear annotation of classes, but this part of the data distribution is far more sensitive to capacity. And we find that essentially what sparsity does is it cannibalizes from certain parts of the distribution to preserve performance on others. So we find that this is true at every level of sparsity, but of course amplified as you get to highly sparse structures. To give you some intuition into what makes certain parts of the distribution more sensitive, we look at what we call Pruni identified exemplars. We look and these are the examples where the predicted divergence occurs between a sparse model and a non-sparse model. And so, for example, this is an ImageNet test set. Can anyone guess the true label? I'm not sure if our Zoom capabilities, I guess we have the Zoom chat. Would anyone venture a guess of what this object is?
The fit.
Like a cap holder?
Pardon? A cap holder?
Yeah, is that?
So this is actually a toilet seat. This is pi, non-pi. How about this one?
That's a glass of Guinness.
Oh, excellent guess. I would agree with you. It's labeled, in fact, an espresso, however, which is perhaps more disappointing, depending on what time zone you're in right now. And we can see here as well. So if you ask what the true label for this is, it's actually a maze. Here it's wool, and here it's a matchstick. And perhaps what you've gathered from this exercise of, thanks to both Bill and I believe it was Peter, of guessing, is that what we see is that these are very challenging examples, and they would be challenging for humans, but they're also challenging for algorithms. So essentially, when you sparsify, you are disproportionately impacting first what you already find difficult to classify. But what's perhaps more interesting is that these are also over-indexed on the long tail of underrepresented attributes. And this is critical for the conversation that follows, because what we're really finding is that we lose the long tail when we remove the majority of all training weights. But if you state this differently, what that's really stating is that we're using the majority of our weights to encode a useful representation for a small fraction of our training distribution. And this means that our low frequency events are very, very costly to memorize and take the bulk of our capacity in these large models. It begs the question of how to feel about this. And I think the answer to that will depend upon what is in the long tail. So we did a human study to classify all the pi examples. And what we found is that this long tail was disproportionately impacted over indexes on two main groups. So one is noisy data points. So data which is improperly structured with corrupted information and may be mislabeled, severely corrupted, or multi-object for a single image task. And this is arguably a misuse of parameters to represent these data points. It's bad memorization. I'll show you some examples. So ImageNet, of course, is a single image classification task. But here's some examples of where the pies. And you can see that these, arguably, in this image, the true label is parallel bars, but the Pruin label is horizontal bars. So this is a case where you could say both are correct. And in fact, this is incorrectly structured for single image classification. Here's my personal favorite. So corn is what you see, and ear of corn is just the top of the corn. Frequently in ImageNet, this amounts to a 50-50 guess as to which one is the top one label. Same with groom and suit. But there's also corrupted and correctly labeled data. So for example, envelope in this image. So it's not clear that you could infer that from the picture. There's another group which is atypical. So these are underrepresented vantage points or challenging because it's very much at the decision boundary between two different classes. And you can see some of those here. So you may have objects outside or unusual vantage points. And how you feel about impeding memorization, which is what compression does, is it depends how relevant these rare artifacts are for the task. To illustrate this, I want to share recent work. So this was led by Areva, and here we were looking at a very interesting setting. We were looking at what we term the low resource double bind. So you have both a limited data regime, but you also have severe resource constraints. So in fact, the main question that we asked when we started this work was trying to understand, in this setting, what's the impact of compression? And it's a very relevant question because most models are deployed under this setting, particularly if you want to serve low resource languages. And what we found was very similar to what we found in the vision case. So we found that sparsity disproportionately impacts performance on the long tail. We looked at this in a few different ways. We structured different evaluation sets. So one we called our prototypical test set, and that was based on shared phrases between the different corpuses. And this is a machine translation task. So we had multiple under-resourced languages, and we only evaluate on these prototypical common phrases. But then we also look in comparison to a random test set. And you can see that the spread of performance and the impact is much more pronounced on the random test set. We also looked at sentence length and some other different characteristics that would tell us how the model is doing on more rare or outlier phrases. But I think this is perhaps really interesting and was surprising to us was that we also found in the setting high levels of sparsity consistently improved generalization to outer distribution data sets. In this way, we were testing a wide variety of different notions of outer distribution, some being dramatically different. So it wasn't so much that we wanted to see would the model perform well, because often these were very obscure, low resource data sets. But we did want to see whether the relative relationship would hold. And we found that for these data sets, sparsity actually helped. It improved generalization. So how to reconcile these two findings? I think this is actually a broader question, is when do we want to curb memorization of rare features? What we observed in this study is very related to the data set in many ways that many low resource languages are using, particularly for low resource African languages, which are based on religious texts. So JW300 is a very specialized religious corpus. And what we explored in this paper and what we attribute the benefits of the sparsity when you do out of distribution generalization is the fact that these rare artifacts in a very specialized data set, which has a lot of religious terms, are perhaps even rarer in other settings that we wish to generalize to. And this is really interesting. It's interesting because whether pruning aids or impedes, it depends on a few different dimensions of what you think is relevant to the task. So for in-distribution considerations, so you want to generalize within your distribution, a lot of it depends on what's the composition of your long tail. If you have a data set like ImageNet where there's many, many noisy data points, sparsity can arguably hold consistent your performance or even benefit because it's curbing the memorization of those data points. But if you have atypical data points, it can have other implications. So one of our other works was characterizing bias when you want to learn an underrepresented group. So a lot of vision problems, you typically want to be able to have good performance, even if the underrepresented or protected feature is not well represented in your data set. And here, pruning can amplify bias because it's impeding the learning of the long tail. So these are some of the in-distribution considerations that we have when we think about what is good and what is bad. But there's also out-of-distribution considerations. So a lot of what our recent work was illustrating is that if you have an out-of-distribution consideration, what is bad and what is good memorization is very dependent on your availability of data and how well that data represents where you hope to generalize to. And if you have very low data regimes, so the data is very different from my training distribution, the data you wish to generalize to, then arguably you do want to curb the memorization of these artifacts. But if it's very similar, very common in big data regimes, where perhaps we can represent more of the data of the distribution we hope to generalize to, this may you may want more capacity to encode this memorization. What's consistent across all these settings is that the cost of memorization is currently exorbitant. So we're using the majority of weights to memorize a very small percentage of our training data sets. And this has far-ranging implications because most of our distributions follow a zip distribution. So if we want to model the world, we need to train models that can navigate low frequency events in a much more efficient way. And frankly, I would argue that our current scaling approach is unsustainable. It's kind of similar to building a ladder to the moon. So if we have these diminishing returns and we're so far away from the type of skills that we wish to impart and the complexity of navigating the world, we need to think about how do we change this relationship between capacity and performance. With that, I'm going to pause. I'm happy. I feel like I left plenty of time for questions and a wider discussion. So I'd love to open up and hear what people think.
Thanks for a great talk. And are there any questions? Please just feel free to unmute yourself and go ahead. Yeah, I can start with my question. Yeah. Oh, Anthony, do you have any questions?
No, you can go first.
No, you can go first. Yeah.
Oh, okay. Sure. So, great. Yeah, fantastic talk. I guess my question is, so much about the theme of this workshop in terms of common sense knowledge and reasoning is about representing that long tail of concepts that would allow machine learning models to adapt to many different situations. And the types of knowledge bases we can get these days, we kind of view language models as a type of panacea for, because they can just encode so much more information that we're doing less extrapolation, more interpolation. But I'm wondering how you think that relates to some of the findings that you have here on specifically how compression interacts with these different categorizations of mistakes and goals.
Yeah, I think that's a fairly broad question. I guess one of the key takeaways is that you lose performance on these rare attributes. So whether those rare attributes are things you want to keep to inform your ability to reason about the world or to navigate low frequency events that might seem intuitive. I mean, we had a great example from the previous talk, Martin, where he was saying that breathing and exhaling is far less common in the data set than murder. And I think that's a great example of a fairly low frequency documented event in our training corpus, but we want the model to acknowledge. There's this interesting, I guess there's two sub-questions there. Is how do we get there? Like, what's an efficient way to do so? And perhaps that's where even amongst this group, there'll be different strategies. I suspect one thing that we have to do is move away from treating all examples equally. It seems very primitive that that's what we do in our typical training setup, is that we press go and then we come back, presumably a few hours later. And that's not how humans navigate the world, right? So we pay more attention to certain things. We have the ability to move forward in space, so we can have various signals about how objects relate to each other. But also we have this ability to zoom in or pay more attention or have saliency to how we navigate. So in that sense, I think a lot of efficiency has to be not abstracting away the data pipeline anymore. And that came up in previous talks as well. But what I mean by that is that we know that a lot of training is in fact spent on memorization, and most of your capacity is spent on memorization. So the dynamics of training are such that your prototypical examples are just learned very early on, and then everything else is spent on this long tail. So that in itself gives a signal about how we should pay attention and spend more time thinking about the long tail. The problem for me is, in fact, your first question, is that how do you disentangle between these components of the long tail, what you care about and what you don't? Because what you're talking about is we care about low frequency events, which are actually vital to navigating the world. But then we also have junk in the long tail. We have improperly structured data. We have bad annotations. And I think that's where we have to figure out, how do we figure out the difference between reducible error and irreducible error? And yeah, that in itself is very challenging. So I'll pause there. But hopefully that at least gave you some of the thoughts that I've been thinking about.
I mean, Bill, you had a question as well, or else I can ask a follow-up.
Yeah, sure. Please go ahead. Yeah.
I mean, I think that was a very insightful answer. I guess the follow-up is, are we even thinking about the right models to get at that question you posed at the end, which is, how do you actually separate what are potentially long tail examples, but generalizable long tail examples from the ones that are just, artifacts that we shouldn't focus on, memorized facts, stereotypes that we actually don't, want to have in there? Is it just a question of getting more data and finding the right way of drawing the connections between long tail events that actually need to be associated? Is it a question of fundamentally changing the way we model weights in these networks? Where I guess should we go from here?
Yeah, that's fantastic. That's why I always try and leave a healthy chunk for discussion, because I feel like that's where you get to the meat of it. Yeah, there's almost two questions in that, because so it's interesting. I think we can do a much better job at adaptive training. I think it's so underexplored, and so leveraging signals early on to at least isolate what we should be thinking about more. In terms of how we disentangle the long tail, it depends, because you've mentioned a third type of long tail there that's more complex, which is bias. And that is actually very tricky, because your notion of bias can change depending on your definition. So if, for example, I mentioned in many different cases of representation bias, you have an underrepresented feature that you want to learn, because you want, for example, your model to perform the same way on different races or different genders. And in that case, you want to learn your long tail. But for example, the example given earlier about women lowering the bar, perhaps you actually want to curb the ability of the model to learn. And so it's really fascinating, because it's almost like a Goldilocks at that point. So it becomes, how do we choose something which is a flexible enough representation to encode these different desirable properties we have? And that's where your question, what is the right representation, I think comes to the fore in my mind. Because if our goal is just to encode the long tail in a more efficient way, that is actually a less challenging goal than this goal of creating a flexible enough representation that we can impose certain constraints on it in an adaptive way. Like we can say, this type of property we want to curve, and this type of property we still want to recall. And that's where it gets interesting, because that's a limitation of parametric models. They're frequency counters. So essentially, we can choose, for deep neural networks, we can either choose to curb the ability to count low frequencies, or we can have design choices which promote. And that's where we have to revisit. Because the other aspect, and I'll mention this briefly, is that because we're so dependent on global updates, we have a very static way of training. We essentially don't have a good framework for things like continual learning, or things to avoid catastrophic forgetting, because again, a global update means that you need to update all your weights at once. You run into issues if you're doing, and you're nodding. So I'd love to hear your thoughts on this. Maybe I'll open it up for the last few minutes, because I want to hear what you think.
I mean, I'd say I agree with pretty much everything that you said. Maybe to not hog the conversation, we can have somebody else speak up as well, and really open it up.
I have thoughts, but it's not very well formed yet, but I'm going to try anyway. So I wonder to what extent the current models, when you talk about generalization, then to what extent is that being able to see a slightly different example but still predict the same answer versus completely, learning well the examples that, okay, not phrasing it really well. is the generalization similar when you train a model on is the generalization that currently happens similar in a way to the way that people generalize, or is it not necessarily generalizing in the same dimensions that people do? So if you have multiple examples that are similar in some way, it's going to learn to solve them. But then if you have something that's I don't know, some slightly differently phrased but similar, it's still not going to
Yeah, I actually think this is like one of the $1 million questions. So it's like so I guess there's various levels to this. One is the ability to generalize from few examples, and there it seems that more data and bigger models is in some ways getting us closer, as long as your training data set is comprehensive enough that you have a rich interpolation space. But at the same time, how sustainable is that? Because of the cost of scaling this, increasing, and to going to more and more different environments and multimodality. And there the question of how do you measure performance on what is slightly different that you haven't perhaps trained on, and maybe the interpolation space is not rich enough, becomes more interesting. And there again, I think our field is very fractured, because how you define different has in fact created different subfields. Like the difference between robustness research and out-of-distribution research is actually, like, where's the boundary? Because robustness is, in a sense, perturbing things so they weren't quite how you had them during training. And then, yes, as you go more, you differ more from your training distribution, perhaps that's where it veers into out-of-distribution. But you can imagine that there's a common underpinning theme there, which is how do you take static models and the degree to which they can adapt. And I think there's been a tendency to think about it in terms of how do you optimize for robustness in your first training of the model. But I actually think the question has to be different, is that how do we create models which we can retrain without completely losing the performance on the first distribution? And that seems to be the area that's both getting finally more research attention, but is also tremendously difficult because of the global update problem. Because we're not selectively updating parts of our representation. The fact that we've delegated the representation to the model means we don't know what parts of the representation to update. So it's a really interesting question.
Yeah, that's an excellent point, that we are finally in the last few years starting to work more on starting with some pre-trained model and then just transferring it to another task. But I think that despite knowing about catastrophic forgetting, I think that not enough work actually goes back to evaluate on the previous tasks or the other tasks that the models performed well on before training on a new data set, and checking whether these this type of knowledge and the skills are still in the model.
Yeah, I agree. I agree. I think I guess that's the beauty of this field, is that I honestly think the obsession with bigger and bigger models is it's a natural cliff, and I suspect then we'll get to the more interesting questions. Because I understand why there's a lot of interest around it, because it's a valuable direction of research to establish the outer bounds of this trade-off, and we should, because it's good to understand these regimes of generalization and what they give us. But I suspect the community will soon turn to the real questions, which is what happens when it's no longer feasible for us to keep on building this ladder, which isn't tall enough to get to where we're going. And one of those is what you're describing. Like, we have to care more about adaptivity of models.
Thanks a lot for your questions and answers. And actually, my question was also about like the relationship between continual learning and the generalization stuff. And I have been working on the continual learning project this summer, and which is very relevant to what you just described. Like, can we do not like we don't want to retrain the whole model, but we wanna fix some generalization errors over the time when the new errors coming in. But Yeah, I have a quick question. Like, do you think it's possible that if we have the signals, like we know like this is our model and we have some generalization errors, but we don't have the correct annotations of such generalization errors. So that we have some error examples, but we only know they are wrong, but we don't know the correct labels for these examples. Can we still fix the model? Do you think it's theoretically possible?
Yeah, it's really interesting. So do you mean in the sense that the model, I guess, do you mean in the sense that the model, the labels may be wrong, but they're also wrong in the test set, so you can still benefit from learning them, but they're not?
Yeah, right. Yeah.
Yeah.
Like let's say we have a model and we put it online, and some user feedback say like this input, the model gives a wrong answer, but we don't have resources for human to label this the correct answer for this input. So I think that would be
Yeah,
wonderful if we have.
I have two slightly different answers. So the first one is just where the label is wrong because there's a systematic mislabeling problem, and it's completely stochastic, the mapping. So it's completely wrong. The input to what the model gives it makes no sense. There it's much easier. It's almost like this is why there's so many experiments with like random perturbations, because it's the easiest case of this noisy. And there I think we can leverage very clear signals across training of how the model struggles much more with these examples. So these are typically the last we learned. The performance on the subset is the worst. The harder case is the ambiguous case of it's a model. The training data was annotated in a way that it's informative, but for human, not sensible. And that's where I frankly see this a lot with our evaluation sets. If the same issue occurred with the evaluation sets, our current way of rewarding progress doesn't reward methods that actually seek this out. So often if you design a method which identifies these and corrects these, it doesn't show up as an improvement on your eval set if it suffers from the same issue. And that's the core of it, is that our benchmarks, if it's being perpetuated throughout, it's hard to show our SOTA progress, if that makes sense. But that's also why I think we need to address the difference between test set evaluation and our desired generalization performance in the real world. And we don't talk about that in machine learning because we frankly prefer the sandbox of test set than this more messy framework that you're talking about of the UI feedback of how was our initial data collection floored. So yeah, it's more gray and ambiguous.
Thank you very much for your insightful answers. And is there any questions from the audience? Okay, thanks again for Sara's talk and very insightful QA session.